My dear students, in last class you have had seen the introductory video of the course, and now let's start with the first topic of the course, that is general characteristics of the transition metals. So dear students, I am Dr. Neeraj Upadhyay, Assistant Professor, Department of Chemistry of Dr. Hari Singh Gaur University. So let's start with the today interesting and learning lecture of general characteristics of transition metals. Let's have a look on the learning objective of the lecture. As we will conclude this lecture, you will be able to interpret and apply the basic concept of transition metals, and at the same time you will be able to investigate and analyze the exceptional behavior of the transition metals. But before that, we must say you must have some basic background or fundamental knowledge of periodicity in properties, molecular forces and redox potential. So let's start with the general definition. As per the definition, elements having incomplete or vacant d orbitals in neutral or ionized state is called transition elements. The properties of these elements lies in between s and p block elements, and therefore they are named as transition metals. By this definition, elements from group 3 to 11, that is from group scandium to group copper, are called transition metals. The last electron of group 12, that is the group framed by zinc, cadmium and mercury, also enters into d sublevel but is not considered as a part of transition series, as neither in neutral nor in ionized state these elements have vacant d shell. Elements of lanthanides and actinide series are also considered as a part of transition series, as their filling starts from d1. Practically, we have three transition series. Elements of scandium to copper frame first transition series, elements of group yttrium to silver frame second transition series, and elements of lutetium to gold prepare third transition series. Since both the definition and periodic properties are the function of the electronic configuration of the elements, so let's begin our study from electronic configuration of the transition metals. Electronic configuration can be characterized as a method of filling of electrons in various orbitals of the atom. A building block is made of according to the increasing energy of the different orbitals. Since energy of orbital of a single energy sublevel in absence of any electric or magnetic field are degenerate, therefore in building block only energy levels and energy sublevels have given the space. You must know about the above principle. Relative energy of these orbitals is decided in terms of the number of radials and angular nodes. Higher the number of nodes, higher would be the energy. For example, 1s has neither radial nor angular node and therefore has the lowest energy, which follow 2s orbital that contain a single radial node. 2p contains an angular node and therefore has higher energy than 2s level. 3s contain two radial nodes and have higher energy than 2p level, and so on. According to above principle, the building block for which we are talking about is shown here. Following above principle, 21st electron that is atom of scandium, enters into D sublevel, which is atomic number of scandium, and therefore scandium is the first element of the transition series. It is important to mention here that energy of 4s level is lower than energy of 3d level in ground state. Difference in energy is very small. The next element, titanium, has electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, and therefore the order continues, and the last element of the first transition series is copper, having electronic configuration of argon, then 4s2, 3d, 4s1, 3d10. First transition is summarized in a table shown below. Looking carefully in the table, you can find that chromium and copper shows exceptional behavior where 4s orbital contain a single electron. In fact, chromium is the first element of the periodic table that shows exceptional behavior in electronic configuration. This is because energy difference between 4s and 3d level are very small, which can get overcome by the exchange energies of the 6 unpaired electrons, and therefore has the electronic configuration 4s1 3d5. And similar is the case with the copper. By making arrangement 4s1 3d5, chromium frame half filled 3d sublevel and become stable. The stability of copper is even more with 4s1 3d10 configuration, which make 3d level completely filled. So a general question raised in mind: why copper is considered as transition element if it does not contain vacant or incomplete d sublevel in its ground state? I hope by the definition you can answer the question. Electronic configuration of elements of second and third transition series is shown on your screen. We can see that niobium, molybdenum, technetium, ruthenium, rhodium, palladium and silver all are showing exceptional behavior with respect to the predicted configuration of these elements. This cannot be solely predicted on the basis of exchange energy. The main cause behind this exceptional behavior is in origin of Aufbau principle. The Aufbau principle is based on energy of orbitals that comes after solving the hydrogen atom problem. Hydrogen contain only one electron, and therefore in solving such problem, electron-electron repulsion has not counted. So on going far from nucleus, nucleus-electron attraction weakens up and electron-electron repulsion with the introduction of very diffused orbital increases. As a result, Aufbau principle in its own form is not able to judge the exact picture of the electronic configuration. Here is the table containing electronic configuration of the third transition series. In this table, as shown in your screen, there are 2 points which need a little elaboration. Only platinum and gold are the exception of Aufbau principle in the third transition series. The electrons of element of atomic number 58 to 71 fill in the 4f cell and therefore are not the part of the third transition series. Although those 14 elements should also be the part of third transition series as they have partially filled d orbitals. But giving space to 14 electrons in this transition series is very difficult, and therefore a new series called lanthanide after the name of lanthanum is framed and are separately written. Since last electrons in such elements is filled in inner penultimate shell and these elements should be placed in the transition series, therefore these elements are called inner transition series. In a similar manner, last electron of elements of atomic number 90 to 103 enters into 5f sublevel after actinum. Their properties are closely associated with actinum and therefore they are called actinides. Detailed properties of these two inner transition metal series will be dealt in the coming modules. Now, on the basis of electronic configuration, following properties of transition metals can be easily understood. So have a look on it. Let's start with the metallic character of the transition metals. Having only 2 electrons in its outermost shell, transition elements has metallic character. They are good conductors of heat and electricity. You might have seen copper wire in your household cables for conducting electricity. Similarly, iron pan for preparing your food. They are malleable, that is, when hammered, it can easily take a shape of sheet. They are ductile, that is, they can be stretched into wire without breaking. Gold, silver, copper are good ductile materials. Now let's talk about the hardness. An alkaline earth metal, transition metals are hard and brittle. Mercury is the only exception and exists in liquid state at room temperature. The hardness and brittleness associate with the covalent bonding in the crystal lattice of transition metal. No doubt, being metal, transition metals also have metallic forces. Generally, unfilled d orbitals provide sufficient covalent character and valence s electron insert metallic character in the lattice of transition metals. Transition metals are key to automobile industry because of the hardness, strength, stability and resistance towards the heat and fire. I have a question for you. Why alkali metals are soft and less brittle than transition metals? Alkali metals in its lattice is framed by metallic forces only and therefore softer than transition metals. Compared to the alkali and alkaline earth elements of neighboring group, transition metals have low atomic volume. This is because incoming electrons is getting filled in the penultimate shell, which is more diffuse and having less electronic repulsion. But at the same time, nuclear charge also increases and attract valence electron to make them closer. As a result of which, the volume of transition metals have lower than the preceding alkali and alkaline earth metals. Because of low volume and increased mass, the density of transition metals become higher. Most of these elements have density higher than 5 gram per cc. Here is a table that incorporates outer electronic configuration, atomic volume and density of transition metals. You can see trend of the atomic volume, that is, volume is decreasing from scandium to cobalt and then increase for copper to zinc, which is because of the increase in the shielding effect or screening effect by the d electrons. Do you know which element has highest density in the periodic table? It's osmium, having density around 22.6 gram per cc. Now let's talk about the atomic radii. I refer you same table for getting similar trend of atomic radii as of atomic volume. It is seen that atomic radii is decreasing sharply from scandium to chromium, and then manganese exceptionally has higher radii due to extra stable d cell, while radii of iron to nickel remains approximately constant and then radii decreases from copper to zinc. This is because successive addition of electrons in the inner d sublabel shield the attractive forces of nucleus to outermost shell of the electrons. Transition metals form alloy. Let's discuss about this. This is because atomic radii of these elements are very close, and therefore improvement in the lattice of one element can be done by insertion of other transition metals. For example, brass is an alloy made mainly by copper and zinc. Steel is another alloy made up mostly by iron and chromium. By variation in the composition of two or more elements, properties of these alloys can be tuned. So, alloys have proud history and future. Our achievement of technological height depends on formation of new alloys of desired properties. Now let's talk about the melting and boiling point of the transition metals. Melting point and boiling point of transition metals are very high. In most of the cases, melting point of elements are higher than 900 degrees centigrade, which is very high in comparison to S-block elements. For example, melting point of lithium is only 108.5 degrees centigrade and of cesium 28.5 degrees centigrade. Melting point and boiling point of first transition series is shown here in the table. You can compare these with the alkali metals. You can see the similar trend like of radii and volume in the melting point and boiling point properties of the transition metal. Generally, melting point and boiling point increases from scandium to manganese and then remain constant from iron to nickel. Finally, it decreases from copper to zinc. Manganese has exceptionally low melting point because of extra stability of its orbital that cause less covalent interaction with adjacent manganese atoms. Zinc, cadmium and mercury are not the part of the transition metals but have exceptionally low melting points. That is, for zinc it is 420 degrees centigrade, for cadmium it is 319 degrees centigrade, and for mercury it is minus 38.5 degrees centigrade. This is because all of them have field d orbitals and therefore have very less or no covalent interactions, while all transition metals have sufficient degree of covalent nature in its crystal lattice. I have another question for you. Why manganese has lower melting point than chromium and iron? Manganese has comparatively stable configuration and therefore have less tendency to overlap with the adjacent atom in its crystal lattice. That's why it has lower value of melting point than expected. As you know, energy required to remove the most loosely electron from an isolated gaseous atom is called its ionization energy. So, ionization energy gives an idea about the ease of removal of electron from isolated gaseous atom. Because of comparatively small size and high nuclear valence electron attraction, the ionization energy of transition metals are quite high. Table on your screen is shown for first, second and third ionization energy for the first transition series. The ionization energy is expected of the elements of the same transition series to increase when going left to right in the period. This is because of decrease in size and increase in nuclear charge of the element when we are going left to right in the transition series. But with increase in population of electron in inner shell, that is in penultimate d sublevels, shielding effect overcome the nuclear attraction. This opposing effect is responsible for only slight change in the ionization energies of the first four elements, that is scandium, titanium, vanadium and of chromium, and the elements of iron, cobalt, nickel and copper. The ionization energy of manganese and zinc is expectedly high because of extra stability of these two elements. Same analogy can be seen for the second and third ionization series of the elements of first transition series. The value of ionization energy in most of the cases lies in between S and P block elements of the same period of periodic table. It is therefore transition metals has the tendency to form ionic compound, but to a lesser extent than that of alkali and alkaline earth metals. At the same time, its higher valency has more tendency towards covalent bonding. So now let's talk about the reactivity of the transition metal. Transition metal atoms are small in size and comparatively have high ionization energy. They also have high sublimation energy and low hydration energy. Therefore, transition metals have a small tendency to react. This makes transition metals inert or noble. Gold and platinum is good example of the inertness of these elements. That's why they are precious too. Unlike atomic form, transition metal ions has high hydration energy and therefore has tendency to form ionic bonds. The hydration energy is attributed because of both ion dipole interaction and high possibility of formation of coordinate bonds between the metal ions and water molecules. Transition metals also act as hard acid and therefore show a strong interaction with water molecule, which is a hard base. Because of these reasons, transition metal ions have high enthalpy of hydration. So even if transition metals is in its pure form or in alloy form shows sufficient inertness, transition metal ions have tendency to form ionic, covalent and coordinate bonds. Now, on the basis of the lecture learned, let's have the summary of the lecture. The elements having partially filled d sublevel in atomic or its ionic state is called d block elements. Their atomic properties are in between s and p block elements and therefore they are called transition elements. They are also situated in between s and p block elements of the same period of periodic table. Like other metals, they are good conductors of heat and electricity. They are hard, brittle, malleable and ductile. They have low atomic volumes and high density. The atomic radii of the elements of the same transition series are very nearby and therefore are used to form alloy. In addition to metallic forces, there's sufficient degree of covalent interaction in the lattice of transition metals that are responsible for high melting and boiling points of the transition metals. Their ionization energies are also high because of small size and high nucleus valence electron interaction. Due to high ionization energy, high sublimation energy, comparatively low hydration energy, transition metals are comparatively inert, while their ions form ionic, covalent and coordinate bonds and therefore they are very reactive. So that's all about the lecture. Thank you very much for listening me.